America is producing some of the cheapest electricity it has ever had, and in some places, at some hours, the grid is throwing it away. Not because the panels failed, not because the sun stopped shining, and not because America suddenly has too much energy. The power is there, the demand is growing. Data centers need electricity. Factories need electricity. The AI economy needs electricity. Households are being told the grid needs more capacity, and yet cheap solar power is still being curtailed. That contradiction reveals one of the biggest hidden problems in America's energy transition. The country has learned how to build cheap solar faster than it has learned how to deliver that solar through the grid, store it for the evening, and connect it to the industries that need power most. This is not a story about solar failing. It is a story about the system around solar failing to keep up, because electricity is not valuable just because it is produced. It is valuable when it reaches the right place, at the right time, through a grid strong enough to use it. And that is the hidden cost of cheap solar. The panel got cheap. The system around it did not. This matters because the United States is entering a new electricity era. Data centers are expanding. Artificial intelligence is increasing electricity demand. Semiconductor plants, battery factories, EV supply chains, electrified heating, and new industrial loads are pushing power back to the center of economic strategy. Electricity is no longer just a utility bill. It is becoming a foundation of national competitiveness. If America wants to reindustrialize, it needs power. If it wants to dominate AI infrastructure, it needs power. If it wants to build more factories at home, it needs affordable, reliable electricity at the right locations. Solar should be a major advantage in that strategy. But there is a difference between producing electricity and delivering useful energy to the economy. A solar farm in the desert does not automatically power a factory hundreds of miles away. A midday solar surplus does not automatically solve an evening demand peak. A low-cost megawatt-hour has limited value if it is trapped behind congestion, arriving when local demand is already saturated, or competing with thousands of other megawatt-hours at the same moment. That is why curtailment is not just an operational detail. It is a signal. It tells us where the physical grid is too weak. It tells us where generation grew faster than transmission. It tells us where storage is not yet large enough. It tells us where electricity markets have not fully adapted. California shows the pattern clearly. During sunny spring days, when temperatures are mild and electricity demand is relatively low, solar output can surge beyond what the grid can absorb. At that point, operators may reduce output from renewable plants, even when the energy itself is cheap. This is not just a California story anymore. It is a preview of what happens when solar becomes a major industrial-scale resource before the rest of the system catches up. To understand the problem, we need to understand what curtailment actually means. On the surface, curtailment is simple. A generator could produce electricity, but the grid operator tells it to produce less. With solar, this can happen when panels are ready to generate, but the system does not need all of that output at that moment, or cannot safely move it to where it is needed. Imagine a factory that can produce millions of units at incredibly low cost. The machines are running, the product is ready, but the roads out of the factory are jammed, the warehouses are full, and the customers want delivery later in the day, not right now. That is what cheap solar can become without enough grid flexibility. Solar production is highest in the middle of the day, but electricity demand often peaks later, especially in the early evening. When people come home, appliances turn on, air conditioning may still be running, and solar output begins falling. This creates the famous duck curve. Low net demand during midday solar production, followed by a steep evening ramp when the sun goes down. The best solar resources are often far from the biggest load centers. Desert land may be cheap, solar irradiance may be strong, but the power still has to move through transmission lines. If those lines are full, the electricity cannot simply teleport to the city, the data center, or the industrial park that needs it. The grid is not just an energy delivery machine. It is a real-time balancing system. Operators must maintain frequency, voltage, reserves, ramping capacity, and contingency margins. Sometimes dispatchable resources need to stay online, even when solar is available, because the system needs flexibility for the next hour, not just cheap power in the current hour. Batteries can absorb midday solar and release it later. That makes them one of the most important tools for reducing curtailment. But storage has to be built in the right places, sized correctly, connected to the grid, and paid for through a market structure that rewards the services it provides. Without enough storage, the system has fewer options. Use the solar immediately, export it, or curtail it. And when transmission is congested, demand is low, and storage is full or unavailable, curtailment becomes the release valve. This is why solar's falling cost does not end the energy transition. It changes the problem. The old question was, can solar become cheap enough to compete? The new question is, can America build the system that makes cheap solar valuable? That system is much more complex than a solar panel. It includes high-voltage transmission, regional coordination, interconnection reform, grid-enhancing technologies, demand response, batteries, advanced forecasting, and flexible industrial load. In other words, the energy transition has moved from a generation problem to a systems engineering problem. And systems engineering is where America is now under pressure. A solar farm can often be developed faster than a major transmission line. Panels can arrive faster than permits. Developers can propose projects faster than grid operators can study them. Investors can finance generation faster than regulators can decide who pays for upgrades. That mismatch creates one of the biggest conflicts in the U.S. power sector. On one side are developers trying to build clean generation and storage projects. They see demand growing, tax credits available, and customers looking for low-cost electricity. On another side are utilities and grid operators who must protect reliability. They cannot connect every project instantly. They have to study power flows, congestion, stability, and upgrade costs. This is why curtailment creates tension. For developers, curtailed solar can mean lost revenue. A project may look profitable on paper, but if it is frequently forced offline during high output hours, the economics change. For industrial customers, curtailment creates a strange contradiction. The region may have abundant cheap electricity on paper, but the customer still cannot necessarily get firm, reliable, deliverable power at the exact site where a factory or data center needs to operate. That contradiction matters because the next wave of American industrial strategy will be electricity intensive. AI campuses do not want theoretical energy. They need firm capacity. Semiconductor fabs do not run only when solar output is high. Battery plants, hydrogen projects, and advanced manufacturing facilities need reliable power quality and predictable energy costs. If America is curtailing cheap electricity in one place while struggling to supply new loads in another, the issue is no longer energy abundance. It is coordination. The cheapest electron in America can become almost worthless if it is trapped behind a congested line. That is the real hidden cost of cheap solar. It is not that solar is too cheap. It is that cheap generation exposes every weak point in the delivery system. This is where the issue becomes geopolitical. The strategic advantage will not only belong to countries with cheap energy resources, it will belong to countries that can convert cheap electricity into industrial output. That means grids become geopolitical infrastructure. A country that can integrate massive amounts of solar, wind, storage, nuclear, hydro, and dispatchable capacity into a reliable system has an industrial advantage. It can support data centers, it can attract manufacturing, it can electrify transport, it can produce clean fuels, it can reduce exposure to imported energy. It can offer companies something every modern economy needs: power that is affordable, reliable, and scalable. Curtailment shows where that advantage is incomplete. If solar output is wasted because transmission is missing, then the country is not fully capturing the value of its own energy investment. If interconnection queues are clogged, then capital is waiting on process. If transformers and substations are delayed, then energy strategy becomes dependent on supply chains that may be slow, foreign, or constrained. This is why the solar boom is not just an environmental story. It is an industrial system story. China understood this connection early. Its clean tech strategy is not only about cheap panels. It is about manufacturing scale, supply chains, infrastructure, state coordination, and the ability to move quickly across multiple layers of the energy economy. But America's weakness is fragmentation. Utilities, states, regional transmission organizations, federal agencies, local communities, developers, and industrial customers often move at different speeds. The result is not a lack of ambition, it is a coordination problem. And in a world where electricity demand is rising again, coordination becomes power. The country that solves curtailment does more than waste less solar. It turns cheap generation into industrial leverage. Still, curtailment should not be exaggerated into a simple failure narrative. A certain amount of curtailment can be normal in a high renewables grid. In some cases, it may be cheaper to curtail a small share of solar output than to build expensive infrastructure that is only needed for a limited number of hours each year. The real question is scale, pattern, and direction. Is curtailment occasional, manageable, and part of an optimized system? Or is it growing because the country is repeatedly building generation without building enough transmission, storage, and flexible demand around it? Curtailment can also be an opportunity signal. If a region regularly has surplus cheap power at certain hours, that could attract flexible loads. Industrial processes that can shift timing, EV charging networks, hydrogen electrolyzers, thermal storage, and data workloads may all help absorb low-cost electricity when it is available. Batteries are already changing the equation. As more storage is added, midday solar can be shifted into evening peaks. Demand response can help as well. Instead of only forcing supply to follow demand, parts of demand can become more flexible. So the answer is not to stop building solar. The answer is to build solar as part of a larger industrial system. That means planning generation, transmission, storage, and demand together. It means speeding up interconnection without weakening reliability. It means treating batteries not as optional add-ons, but as grid assets. It means recognizing that transmission lines are not just local infrastructure. They are national competitiveness infrastructure. Most importantly, it means understanding that the cheapest power is not the power with the lowest production cost. It is the power that can actually serve the economy when the economy needs it. That is the lesson curtailment is teaching America. But the next battle is harder. It is the battle over grid architecture. Can America build enough transmission to move power from resource-rich regions to demand centers? Can it deploy enough storage to shift solar from midday to evening? Can it reform markets so flexibility is properly valued? Can it connect projects faster? Can it build the transformers, substations, and control systems required for a more dynamic grid? These questions will decide whether cheap solar becomes a full industrial advantage or a partially wasted resource, because energy abundance is not measured only by what a country can generate. It is measured by what it can deliver. The United States is not throwing away solar because solar is useless. It is throwing away solar because the rest of the system has not yet caught up to the speed of the technology. That is the hidden cost, and it is also the opportunity. If America solves this, curtailment becomes less of a warning and more of a transition phase. Cheap solar, paired with storage, transmission, flexible demand, and smarter markets, can become one of the foundations of a more competitive industrial economy. But if America ignores it, the country risks building power it cannot fully use, while factories, data centers, and households still face rising pressure on the grid. The future will not be won by the country that installs the most panels alone. It will be won by the country that turns cheap electricity into reliable economic power. Because the cheapest power in America is not the power that gets produced. It is the power that actually reaches the economy when the economy needs it.